And we're allowed to get away with this simplified explanation because we're going to use these devices according to a set of rules that allows us to think of them as voltage-controlled switches. They're actually not quite so simple. But if we use them according to these rules, they actually behave just like voltage-controlled switches. Okay, so what we're going to do is we're going to build logic gates sort of according to the following formula. We're going to have the output node of the logic gate. So here we have an output node. And then down here we have a ground node. So this is the source of 0 volts. Think of this as the 0 volt power supply. And up here we have the power supply node, which we're going to call VDD. Okay, and so this is our source of 1. Whatever the power supply voltage is. And the way we're going to build our logic families is we're going to use these voltage-controlled switches to build some sort of switching network where we're only going to use P's between the power supply node and the output node. And we're only going to use N devices in the switching network, okay, between the output node and ground. And then we have, so we'll see, here's an input, an A input that's going to some gates inside of the pull-up network. So this is called a pull-up. And this switching network is called the pull-down. Why do we call them pull-up and pull-down? I mean, they're very appropriately named. So what happens is if I close enough of the voltage-controlled switches up here, what will I end up doing if I can make a conducting path between the output node and VDD, what will happen to the output node? It gets pulled up, as the voltage gets pulled up until the power supply rail. In other words, if there's a conducting path of these voltage-controlled switches that connects this node and this node together, this node will get charged up by the power supply. How about the other way? Suppose there's not a conducting path up here, but there's a conducting path down here. Okay, then what happens to the output node? It gets pulled down. So this is called the pull-down network because its job is to discharge the output node. And this is called the pull-up network because its job is to charge up the output node, to make the output voltage high. Now I'm going to start showing you how to actually use these voltage-controlled switches to build interesting logic functions here. But that's the basic plan that we're attacking. Okay, so think of these voltage-controlled switches. I'm going to show you a simple model. They're either off or they're on, and if they're on, if the voltage-controlled switch is closed, then there's a certain resistance to the channel. In other words, it's not like it's a really great wire between the output. There's like a little resistor in here. And that you're basically discharging or charging up the output node through this resistor, which means it takes a little bit of time to do it. In modern circuitry, on the order of tens of picoseconds to charge and discharge this node. Okay, and notice that the bulk terminals here for both the N device and the P device are connected to keep the diode, PN diode junction reverse biased.